So yeah, without further ado, Chris Welty.
Okay, I think you're good.
Thank you. Yes, you might.
All right, thank you, Todd, and a round of applause for Todd. And I don't know if you guys have any idea how much work goes into setting something like this up, but all the people who are involved in making this possible really deserve your gratitude, because that's really why they're doing it. Okay, you saw the highlight of my career there, being part of the Watson team. I wasn't the team lead. That was David Ferrucci, who you saw in that video, the guy with the mustache. I was on the leadership team, which is a slightly different thing. Anyway, it was a great time. It was a great project. But I left IBM this summer and joined Google Research. That's where I am now. And so lots of geeky references here, because ultimately that's really what I am. So a little bit more of an introduction to me, and for those of you who don't know me, which I believe is most of you. Personal history in which I am the savior of the universe. So I worked on Watson, as you just saw the video clips. I joined IBM Research with a background in artificial intelligence and in natural language processing. And as a scientist, what I was working on was natural language processing. And I was responsible for this very particular kind of nuanced thing about trying to join together information that's in a structured form, like in a big database or knowledge base, the way AI in the 80s envisioned intelligent systems would be realized, with natural language processing. Understanding natural language and answering questions in the case of Watson, or acting on it in the case of your phone. I've been heavily involved as one of the founding members of the Semantic Web community. The Semantic Web is a technology that kind of combines the idea of databases with the web, the idea that identifiers should be universal across the entire planet, across the web, and that information can be, once you have this universal notion of an identifier, you can link things together. And you'll hear a little bit more about how that matters in the next talk that Todd will give. And then finally, my original research area was something called Ontology, and I'm not really going to get into that, since I assume this audience is not experts on that. So in the original Star Trek, one of the memes of Captain Kirk was that he was always getting his shirt torn so you could see his chest. For me, it was something similar, using explicit semantics to improve performance. So you can see the analogy there, I'm sure. And again, this is what I'm trying to say, that we've historically in artificial intelligence believed that manually curating our knowledge, rules that we follow when we know something, and bits of information and facts that we associate with the knowledge that we actually exercise when we interact with the world, that this is going to be the key ingredient to intelligent systems. And that did not turn out to be the case. However, just because it isn't the key didn't mean that it wasn't important. And it was a very important part of Watson. In fact, and I'll explain more about what this graph means later in the chart, but just to toot my own horn here and say that the work that I did had about a 10% overall impact on the performance of Watson in winning the Jeopardy. So the important really lesson here, for those of you who at least have some familiarity with the history of artificial intelligence, is that this kind of explicit semantics that we believed would be an essential part of intelligent systems is important, but it isn't the only thing. And there's a lot of other systems and a lot of other parts of Watson that can claim also to have had that much impact on our performance as well. And that's me celebrating when we beat the crap out of Ken and Brad. But the world has changed. Oh, okay, the top of my slide is above there, but that's the Elvish. EMR Prestar Ein. The world has changed. The world has changed. It's changing very rapidly. It's always changing. And the way in which it's changing that I'm going to focus on is cognitive computing. And so this is the story in which not only am I the savior of the universe, but I'm also the inventor of cognitive computing. And here's how that story goes. So in 2012, I gave a keynote talk at the World Wide Web Conference. And it was right after Watson. And I wanted to give a kind of message about how Watson, the lessons learned from Watson impacted the web, because that's what people at that conference were interested in, but also some more general notions about what Watson has to say about computer science. And I outlined these three things, and I'm really only going to talk about the first one, which is what I meant when I invented cognitive computing, which ended up not actually being what IBM meant. So the idea I wanted to emphasize was that what we were seeing, and what Watson was an example of, although I say here in this longer explanation that we didn't invent it. So this had been going on for quite some time, and we were maybe one of the more famous and prominent examples of this new paradigm of computing. And the elements of this new paradigm that I really thought were important, a few of those got picked up by the IBM cognitive computing message, but not all of it. So this is the sort of official IBM message on cognitive computing. And there was a team of people that I was part of that met for a few days, and we tried to distill out of the lessons learned from Watson, and of course also the sales and marketing and strategy pitch that IBM wanted for itself in order to craft a message that could be easily relayed to people, and that's what ended up as cognitive computing. So for IBM, cognitive computing is a technology that expands human capability, so it augments our own cognitive capability, the way a telescope makes it easier to see things that are far away. So a telescope doesn't do anything unless someone's looking through it. And the idea of a cognitive computing system is that it's not going to do anything unless there's a person behind it, but it will amplify your abilities. That it will learn, it will get better, it will adapt to you as a user, it will adapt to your environment if it's changing, and so forth, and that it interacts with us in a natural way. In particular, natural language, also speech. But that's not really what I meant. And so what I'm going to talk about today is what I meant and exactly what I think cognitive computing is all about and how it affects you as entrepreneurs and how it affects business as a whole. And I think these are important lessons. So the first thing I'm going to just say is that cognitive computing systems, they're built. Someone's got to build them. And we generally call a systems builder an engineer. So we've added yet another kind of engineer, a cognitive systems engineer. And the most important, I think, the defining element of what a cognitive system or cognitive computing system is that it's a computational system in which it can fail and still be useful. It's actually far easier to think of what the company I now work for, Google, does, which is web search primarily. I mean, they do a lot of things, but web search is clearly the hallmark of Google. Web search is something without which we would not be able to use the web. But it doesn't always work. Sometimes it fails miserably. Sometimes it fails like the Toronto question, right? I mean, sometimes you know what you want, you know it's out there, and you just don't get it. You can't figure out how to express yourself to a keyword search engine. But you would not be able to use the web if it wasn't there. So the fact that it is fallible doesn't take away from our understanding and appreciation of its value. And This, I mean, for those of you, I know not all of you are computer scientists, but for those of you who are computer scientists, you should know that this is a dramatic shift from traveling salesman problem, okay? This is not a deterministic answer to a problem. This is understanding the notion of value, and that's where I'm one of the key things that I'm going to focus on. So you have to know how to improve a system over time without expecting that it's going to be perfect. And there are a lot of people who claim to be doing cognitive computing today who don't quite get this. A cognitive computing system should not ever strive for 100% perfection, 100% accuracy, 100% precision, whatever you're measuring. The essential nature of cognitive tasks is that no one, no entity, no agent is going to be perfect at performing them. But you have to be able to answer this question if you're going to engineer a system. For people where it's less important that we answer this question because we believe ourselves to be cognitive agents. But for artificially created systems, we have to be able to answer the question, is it better? And there's very important engineering reasons for doing that. So in order to kind of tell that story, I invented the 9 pillars of cognitive systems engineering. And you can see from the picture here that it's very cleverly arranged so that any one, you can see the 2 pieces on top, they're need each other, but they're not connected. So if you take out any one of those 9 pillars, the whole thing comes crashing down. That's important. You have to assume gravity. So the first 3 pillars are measure, measure, measure. The second one, measure, is more important than the first one, but less than the third one. Testing for alertness. Okay, so this is really critical. We had to do this in Watson. We have to do this now at Google and almost every application that Google makes. Measurement is critical. Why is measurement so important? Because when you make a change to an imperfect system, let's say you're writing a question answering system and it gets a question wrong. And you look at it and say, how could you have gotten that question wrong? Everyone knows Toronto's not a US city. And so you go through and you look at all the algorithmic reasons why you got that answer, and you say, okay, now I've got something that's going to fix that. And you run it through, and indeed, it gets the right answer, which was Chicago for that question, and you think, okay, great. And now you run it on 6,000 other questions, and you get 90% of them wrong, all because of this little fix you made in order to get the stupid Toronto question to answer right. When you make algorithmic, data, any kind of engineering change to your system, you have to be able to test it holistically to see if that change is making your system better. This is critical. And this is a real 90-degree shift in the way computer scientists have been approaching problem solving before that. And finally, just a little bit of it, or not finally, but just a little bit of observation here. If you have a system that's performing above 0.8 on some problem according to your metric, then something's wrong, okay? It's a pretty good heuristic, pretty good rule of thumb that either your metric is too easy, or you're lying, or the way you're actually measuring it is invalid. Quick question?
Notion of cognitive systems requiring measurement is sort of at right angles to traditional CS systems or engineering or approaches to software development.
Yeah, algorithms are tested on correctness, not typically against metrics. This is a completely different thing. So we're running, in this case of question answering, you could imagine a fairly easy metric is how many. Take a set of 10,000 questions and see how many you're getting right. And every time you make a change to the system, run against that set of 10,000 questions and see if the percentage you get right changes. Okay? That's not analyzing an algorithm for correctness, which was kind of the traditional computer science approach to algorithm design. All right, and the second, the 4th through 6th pillars of cognitive computing are data, data, and finally data. You know, if you haven't gotten that message, and believe me, there are traditional information technology companies that still today don't understand how important data is. But you can't do anything without data. If you're building a cognitive computing system for a customer, you need your customer's data. You cannot build the system the way, again, computer and software engineers used to build systems by gathering requirements, analyzing the requirements, coming up with the design, back and forth, design, finalize, go to implementation, and this kind of waterfall model approach does not work for cognitive systems. You need the data. You have to have the data in-house, on your desk. You've got to be able to run analysis over that data over and over and over again. It cannot work if you're in the dark about the data. It's simply impossible. We were able to build Watson because fans of Jeopardy put every question ever asked in the 30-year history of the show on the web. So we had 250,000 questions with what the right answer was. That was data that we had. We had Wikipedia. We had other reliable sources of web pages, factual web pages. That data we had, and we just never stopped running analysis and algorithms on that data. That is how we won, and no other way. And finally, just a little controversy, just to stir things up a little bit. I know everyone's worried about privacy. Google is just probably, they'll come down on me for even saying this, but my personal opinion, this is not Google's opinion and not IBM's opinion either, but my personal opinion is that people are too worried about privacy. And if you're familiar with HIPAA, it's the Health Information Privacy Act in the United States, and most countries have something similar. It's so incredibly strict. If you have HIPAA data, if you have someone's healthcare data that has not been anonymized, in other words, that actually you can find out who the person is, you have to be in the same room as the data. That's the law. That's ridiculous. And people are dying because medical researchers can't get access to the data that if they analyzed, they would find cures to things. Now again, I want to stress that's my personal opinion.
Is that
and
IBM Watson doing medical diagnosis? After Jeopardy, that's what it did.
I'm just not going to talk about what IBM did after Watson, after Jeopardy. All right, the last three pillars of cognitive systems are truth, truth, and finally truth. So what is the truth? That's a quote from Sophie's Choice with my bad attempt at mimicking Meryl Streep's accent. I told you about metrics and I told you about data, but in order to actually run any of these metrics, you have to know what, in the case of question answering, you have to know what the right answer is. Okay? That's the sort of truth. Now, Jeopardy questions are designed, they're engineered, literally, to have a right answer. One. That turned out to be really important in making it possible to build a cognitive system that was capable of answering those questions. But now, when we're talking about the web, when we're talking about just no restriction whatsoever, in fact, trying to interpret keyword queries as questions, this becomes much harder, understanding whether or not a question is an opinion. What's the truth if you were to ask who's the greatest basketball player of all time? I mean, what's the right answer to that question? Now, Todd is going to talk a little bit about how you can gather information like that from people and how important a role people actually play in gathering the kind of information that cognitive systems need in order to measure how well they're doing. So what does it mean for it to be right? Because these are cognitive problems like understanding whether if you're interested in one video means you're interested in another video. How do you make that determination? Somebody's got to tell you. A person's got to tell you. And as it turns out, having just one person answer that question doesn't give you enough information. So those are the 9 pillars of cognitive systems engineering. data, 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 truth, 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 and measure, measure, measure. So now you're probably wondering, how can you actually build a cognitive system? Well, I'm glad you asked, because I just so happen to have the 12 steps of building a cognitive computing system right here. Back when I was in college, when the David Letterman show was first on the air and was still funny, we used to really revel at the fact that when a joke didn't really come off, David Letterman would just keep repeating it until it became funny. So in that vein, the first 3 steps of the 12-step program are explore, explore, explore. So this goes right along with what I was saying about the data. The reason you need the data in order to build a cognitive system is that you have to be able to explore it. Building cognitive systems, cognitive computing systems engineering is data science. This is analyzing data and trying to find a sort of a signal between something you observe in the data and the thing that you want the system to do. Okay, in the case of search, Google's algorithms don't really understand what you're after. What they're trying to come up with is a way of computing correlations between things, doing statistical analysis, some amount of language understanding, some amount of understanding what people in your region are interested in order to figure out what the best match is between your query and a set of web pages. And they do that, we do that, by constantly analyzing the queries people make and how they click on the different results and so forth, in order to understand the relationship between queries and search results. And so this is really an exercise in exploration through a large set of data. And now the next set, and I really can't stress this enough, you have to be willing, as a consumer, as a customer of a cognitive computing system, and as a builder of one, you have to be prepared to fail. You have to be prepared to fail way more often than you're going to succeed. That is the essential nature of building cognitive systems. This is an exploration through a space, and you're going to try a lot of things, and most of them are going to fail. During Watson, I was one of the developers, not the only one, but one of them, and about 2/3 of the things that I tried actually worked. That's because I was the best. You have to be able to accept that you're going to waste money. This is another big change. Traditional software engineering environments, they can't accept that someone's going to work for a month on a piece of code that doesn't get checked into the final product. But I worked on it for a month. Yeah, but it doesn't have impact on the metric. It doesn't go in. Absolutely. If it doesn't impact your metric, it doesn't go in. I don't care how long you spent on it. And I was telling some of the people earlier, it took me 6 months to get one of the things that I contributed to Watson. 6 months it took me before it was finally admitted into the system. It took me that long to finally find the signal that it actually grabbed to start having impact. And then the last 3 are combine, combine, combine. And so one of the really important things to understand about all of the different cognitive systems that are out there. So you've got recommender systems, systems that say, you know, you just bought this product and people who bought that also bought this other thing, or based on your personal preferences, I think you might like this, or watching videos and getting recommendations of what to watch next, or searching the web for images. These are things Todd's going to talk about next. Web search, driving a car, understanding speech, answering questions. These are all examples of cognitive systems. And they all work by combining a lot of, in many cases, pretty simple algorithms. But many of them, and they all do slightly different things. I mean, there's no way that we know right now for a machine to understand natural language. The thing that makes Jeopardy hard for people is just knowing all that stuff. But for the machine, that's trivial. What's hard is understanding the question. And we do not have algorithms that completely understand English. We're nowhere near that. What we have are ways of doing data analysis, ways of correlating and connecting terms in a question to terms in a document, and recognizing when a sentence seems like it answers the question without really understanding or without completely understanding either of them. And so we do this by combining lots of different algorithms. In the case of Watson, there were over 100 different algorithms. For the most part, these algorithms didn't know about each other. They didn't consume, they weren't pipelined together. There was a pipeline, but it was different. The algorithms that actually did the heavy lifting of figuring out what the answer to the question were, these did not really communicate with each other. They were combined using a fairly simple machine learning technique. Oh, this is the last one, the last of the 12 steps. Last 3 of the 12 steps. Follow, follow, follow. So this is what we in the Watson team called our experimental methodology. We would take a version of the system. This is a software system. So we would freeze the software system. We would run it on a set of data. And now any one of the members of the team who made any kind of algorithmic changes or data changes to the system would make those changes and then run the whole system again with the new changes on the same questions. And then we would compare the performance of the two systems. And if the new version performed better, then that was going to be our new version of Watson. So we called that a follow-on experiment. We would establish a baseline roughly every month. At the beginning, it was every week, and as the system became more complex, it was every month. We would freeze that system, and then that frozen version of the system could not be touched, and we would then start making changes, testing those changes based on whether or not they improved performance. So this kind of methodology of freezing and then doing follow-on experiments is a very important part, and all of the cognitive systems that I've described to you work in a similar way. But it all leverages off this idea that you have to have a metric. So let me, I have time to explain the metric we use for Watson a little bit. So one of the important things about, and really what ended up being one of the more interesting things about the Jeopardy problem, was not just answering questions, but understanding when we believe the response was correct or not. We call that confidence. This is important for Jeopardy because when you get the question, you choose whether to buzz in, whether to answer it or not. You don't have to answer every question. So you're not rated on your overall question answering ability, but rather only on the ones that you choose to answer. So what we made up here was a metric. It took us a long time to get the metric. And metrics, as I told you, is one of the pillars of cognitive systems. So you have to believe your metric. Your metric has to correlate with what you actually want the system to do. It says since we couldn't play games of Jeopardy over and over and over again every time we made an engineering change to the system, we needed something reproducible. And so what we came up with was what you see here. The x-axis is the percent of the questions that you answer. And the y-axis is the precision, the percent of the questions you choose to answer that you then get correct. The little cloud of dots there is human performance. So that is every person who ever won a game of Jeopardy. That's their performance according to this scale. So the average game winner answers about 50% of the questions and gets about 90% of them right. And the red dots are Ken Jennings' games. He's a freak. I mean, to win a game of Jeopardy, you got to be pretty good already. And then Ken Jennings has won more than 70 games in a row. Just really phenomenal. So the lines that we have there are Watson's performance, and that's the first version of Watson, the brown line there, which, to use a technical term, really sucked at question answering and really sucked at confidence estimation. So confidence estimation is basically the ability to say whether you're right or wrong. The idea here is that if you were doing confidence estimation perfectly, this line should be a diagonal with a slope of -1 that goes up to the top. Because if you know for every question whether your answer is right or wrong, I mean, this is different than knowing the answer. Okay, producing an answer and then knowing whether it's right or wrong. If you knew that perfectly, you would have a much different line than that one. And you can see that orange line, that was the first version of the system that actually convinced us that we could do this. There's a pretty significant jump in the overall number of questions it gets right, but way more important than that is we actually started solving this confidence estimation problem. So Watson was pretty good at knowing whether it had the right answer. And you can see progress. Every successive line was 3 months after the previous one, and you can see how the increase starts to fall off there. So the last 3 lines, I think, is a year. No, it's 6 months. So I think it's probably more like 9 months. No, it's a year. No, it's a year. So it's a year. Those top 3 lines was a year of effort. From the brown line to there was 3 months. So I believe that is characteristic. I've talked to a lot of people who are building cognitive systems. Now that I'm at Google, they have a gazillion systems that can be categorized as cognitive systems, and they all have this flavor. You get to a certain point where there's almost like a fundamental barrier, like the speed of light, that you feel like you're just getting more and more incrementally closer to, and the more amount of effort you spend, the less it seems to pay off. Okay, so just to sum up, I think this is the key characteristic of cognitive systems, that they're computer systems that do something and they can be wrong, but they are right and useful often enough that we're still going to use them. And so in order to build them, you need to have a pretty good understanding of a metric so that you can measure its performance. You need to understand what right and wrong is with respect to the problem you're solving, and you need a lot of data. So I will stop there and take some questions. How much time should we spend on questions? 5 minutes?
So I have 2 questions. The first has to do with philosophy. You said that you're into ontology. So what kind of emotional responses have you built into the system? Because as I understand, if you have to be wrong, there would be some questions that might offend the person who's asking those questions. So it has to, so the machine has to respond in a way that it does not offend the other person, give the right answer, and still be, in the bounds of human morality.
Okay, so for Jeopardy, this was not a problem because the questions were sort of already designed to be non-offensive. That was.
Just repeat or summarize.
Oh, sure. What did we do to account for the fact that you don't want to offend somebody with the answer to your question? So the Jeopardy questions were not very controversial. Now that I work at Google, this kind of thing is a big problem, but it's a really long and involved answer. So why don't we talk about it after?
The second one is, I understand that there is this knowledge base which has like 26 billion facts. I'm sure you're aware of knowledge graph.
The knowledge graph.
So have you been able to incorporate that, because that would really improve the amount of learning that the machine can use to give outputs out of. So you've been able to incorporate that into the system, or you developed your own set of...
Okay, well, just to be clear, knowledge graph is something owned by Google, and Watson is something owned by IBM, and so no, I have not combined them. But at Google, we do use the knowledge graph quite heavily, and that's basically my principal area of research is going to be how to harness the knowledge that's in the knowledge graph to make search better. Thank you very much. I will...